Hi, my name is Darian, and I'm here to talk about Wi-Fi. So this talk is titled Wi-Fi Crash Course, a noob's guide to key terms and concepts. The goal here is to give a beginner's-friendly overview of the Wi-Fi protocol. I'll try to cover as many key concepts as I can in 30 minutes, and hopefully this will serve as a crash course in the Wi-Fi protocol. Just a heads up, there's a lot to cover, so this presentation goes fast. But this is being recorded, so you can always rewind and rewatch. So, what's my background? I was a senior embedded software engineer at Espressif. I worked on the software platforms team for over 7 years, mainly working on the ESP-IDF SDK. Now, as a disclaimer, I'm not an expert in Wi-Fi, but I figured what better way to do a noob's guide in Wi-Fi than have another noob teach it. So, what am I going to be covering? Firstly, I'll start off with what exactly the terms Wi-Fi and 802.11 mean. Then, the differences between the wired and wireless mediums. Next, some basic Wi-Fi topologies such as BSS and ESS. Then an overview of what MAC frames are, followed by management operations such as authentication and association. Next, we'll take a look at medium access methods, primarily the distributor coordination function. And finally, some physical layer concepts such as channels. And we'll round off with some further topics and resources. Without further ado, let's begin. So, what exactly is Wi-Fi? In short, Wi-Fi is a technology for wireless local area networks. Well, what is a local area network? In the world of computer networking, networks are classified by spatial scope. So at one end, we have nano networks, and these are on the scale of nanometers. At the other end, we have wide area networks, so these span countries and continents. Local area networks, on the other hand, otherwise known as LANs, are typically at the scale of hundreds of meters. So think residences, offices, schools, etc. The most common technology for wired LANs is Ethernet, and for wireless LANs, otherwise known as WLANs, the most common technology is Wi-Fi. So the terms Wi-Fi and IEEE 802.11 are typically interchangeable. You would likely hear the term Wi-Fi more because it's not a mouthful to say. However, these two terms technically mean different things. To be specific, the term IEEE 802.11 actually refers to a set of protocol standards for implementing WLANs. These set of protocol standards are created and maintained by the Institute of Electrical and Electronics Engineers, otherwise known as IEEE. Wi-Fi is a trademark owned by the Wi-Fi Alliance. Any 802.11 device that wants to be called a Wi-Fi device must be certified by the Wi-Fi Alliance. This certification basically ensures interoperability between different vendors. However, these two terms are typically interchangeable because most consumer devices that support 802.11 are also Wi-Fi certified. The 802.11 protocol has been updated over time to support higher speeds and new features. However, if you try to search for a list of 802.11 versions, you'll be met with a bunch of confusing suffixes. To understand these suffixes, you'll need to know the difference between the main protocol standard and protocol amendments. The main protocol standard is the official document describing how a WLAN should be implemented, and each version of this document is labeled 802.11 followed by the year of the standard's publication. So, for example, here's 802.11 1999, then 802.11 2007, and 802.11 2012. However, those improvements to the protocol standard come from amendments. An amendment is a proposal describing a particular improvement to the Wi-Fi protocol. When a proposal gets adopted, it gets published as an amendment document. Amendments are labeled 802.11 followed by one or two letters. So here, for example, we have 802.11a, 802.11b, and basically all of these are amendments. Once an amendment gets adopted, it will eventually get incorporated into a future version of the main protocol standard. So here, for example, 802.11n added multiple input, multiple output support. It was adopted in 2009, but this wasn't incorporated until the 2012 version of the main protocol standard. So here's a table showing particular amendments, the year of adoption, and the protocol version that they were eventually incorporated into. However, these suffixes don't make it easy to track what changes were made. Thus, the Wi-Fi Alliance has come up with a simplified generational numbering scheme. Each generation is tied to a particular amendment, and as you can see, the Wi-Fi throughput has only increased over the past couple of decades. Now that we know what Wi-Fi is, let's briefly look at the differences between wired and wireless LANs, and what are some of the benefits of going wireless. Given that we're talking about LANs, let's use Ethernet and Wi-Fi as examples. Firstly, the wired medium can be a unicast. This means when a node transmits a signal down the cable, only the node connected to the other end of the cable receives the signal. Secondly, signal delivery in wired mediums is reliable, meaning if a signal gets sent down the cable, we're relatively certain that it gets received correctly at the other end. In the case of Ethernet, reliability is achieved by using differential signaling with twisted wire pairs. So here, the green pair is one signal, the blue pair is another signal, and so on. Thirdly, wired mediums can be full duplex, meaning that data can be transmitted and received simultaneously. So in an Ethernet cable, the green pair handles the transmit signal, and the orange pair handles the receive signal. However, in the wireless medium, things get much more difficult. Firstly, wireless is inherently a broadcast medium, meaning whenever a node sends a radio signal, any other node within range can receive it. Secondly, wireless is a half-duplex medium, meaning that at a particular frequency, only one node can transmit at a time. This is because simultaneous transmissions from another node will cause interference. And thirdly, wireless is an unreliable medium, meaning if we transmit a radio signal, we can't be sure that it gets received correctly on the other end. This could be due to signal attenuation or interference. But regardless of the wireless medium's complexities, Wi-Fi has still become ubiquitous in most home and office LANs, so there must be some major advantages in going wireless. Firstly, WLANs provide great device mobility, meaning you can move your device around and still remain connected. It's also easier to deploy as you don't need to lay any physical cables, and because it's wireless, it has greater flexibility. Adding or relocating new devices to the network doesn't require any cables to be rerouted. And finally, the ease of deployment and flexibility typically means lower cost to deploy and maintain. However, WLANs also suffer from some drawbacks. Firstly, because the wireless medium is half duplex, the throughput is typically lower than a wired medium. Secondly, it's less reliable due to interference and signal attenuation. Lastly, it lacks physical security, as anyone with an antenna nearby can receive those radio signals. But Wi-Fi mitigates some of these drawbacks, and the complexity of Wi-Fi mostly comes from this mitigation. Now, let's dive into the implementation details of Wi-Fi. And to start off, let's take a look at network topology. Firstly, let's clear up some basic terminology. The first term to cover is stations. In Wi-Fi, any device that implements the 802.11 protocol is known as a station, or STA for short. More specifically, the part of the device that is considered the station is the Wireless Network Interface Controller, or WNIC. Each station has a unique MAC address, and the WNIC will typically have an antenna and radio for wireless connectivity. The next term is service sets. Whenever multiple stations are grouped together to form a logical network, this is known as a service set. Each service set has an identifier, otherwise known as the SSID, and the SSID is typically a natural language label. Basically, SSIDs are the network names that you see when scanning for nearby Wi-Fi networks. So, for example, these three stations are grouped together as a service set, so they have their own SSID. Likewise with this service set and their own SSID. So, if a service set is a grouping of stations, what are some of the different ways we can group them? This is when we get into topologies. The first topology to look at is the Infrastructure Basic Service Set, otherwise known as a BSS. This is the topology that you most likely use on a daily basis, and it's found in most small office and home office networks. The BSS is made up of a single access point, otherwise known as an AP, and one or more stations. The AP itself is a station, but it also has added capabilities similar to a network switch. This means all stations only communicate directly with the AP. The AP is responsible for forwarding all communications to the correct destination. So here we have a BSS, and that BSS contains an AP and stations K and L. If station K wants to communicate with station L, then K must send the data to the AP, and the AP is responsible for forwarding that data to station L. Each BSS has a unique identifier, known as the BSS ID. This is typically just the MAC address of the AP. An important thing to note here is that the BSS ID is not the same as an SSID. Those are two different identifiers. If a station wants to join a BSS, they must associate with the AP. And stations that are already part of a BSS are known as associated stations. So here, stations K and stations L are associated stations, and if station J here wants to join the BSS, it must associate with the AP. And the last BSS concept to cover is the Basic Service Area, otherwise known as the BSA. This is basically the coverage area of the AP. All stations must remain within the BSA to stay connected, but they are free to move inside the BSA. The borders of a BSA are determined by a signal strength threshold. However, this means that the BSA is fluid as many factors can dynamically influence signal strength. So, what does a BSS look like in practice? In this example, we have two adjacent apartments, each with their own Wi-Fi networks. So, because they're each their own networks, they have their own SSIDs, and each network contains a BSS. You'll notice some overlap between BSA1 and BSA2. This is why you can see your neighbor's Wi-Fi networks. and with AP1, it's connected to a network switch so that wired and wireless devices can form a single LAN. And there's also a router to handle internet connections. Basically, if you buy an all-in-one router, it'll typically include an AP, switch, router, and even a modem. In summary, the BSS topology is centered around an AP, but because the BSA depends on the AP's coverage, a BSS is limited in coverage area. I'm sure you can think of instances in your home where particular areas have poor Wi-Fi coverage. To address this problem, Wi-Fi also supports grouping together multiple BSSs into something called an extended service set, otherwise known as an ESS. If you've ever used a roaming Wi-Fi network, chances are it's an ESS. So, the definition of an ESS is two or more BSSs connected by a distribution system, otherwise known as a DS. The main benefits of an ESS is that stations can roam over a large service area and still remain connected. To achieve this, there are overlapping basic service areas, and together they form an extended service area, otherwise known as an ESA. And as the station roams around, they'll reassociate with the AP that has the strongest signal. The distribution system is basically a system that interconnects the APs of each BSS, and it can be wired or wireless. The implementation of the DS isn't specified by the Wi-Fi protocol, but the DS must offer particular services. These services include tracking which stations are associated with which AP and forwarding data between APs. Because the ESS is a single service set, all of the BSSs are under the same SSID, meaning they belong to the same logical network. However, each BSS still has their own BSS ID, and from a user's perspective, they will remain connected to the same Wi-Fi network while roaming, and never even notice that they've switched APs. Let's look at an ESS in practice. Let's say we have a Wi-Fi network for an office, and this network contains 3 BSSs with overlapping BSAs. So here's BSA1, here's BSA2, and here's BSA3. Now, because they're all part of the same network, they all share the same SSID. As station A enters BSA1, it can now join the network by associating with AP1. And if station A here wants to communicate with station B, the data flow is as follows. Station A will send the data to AP1, AP1 will then forward that data to AP2 over the distribution system, and then AP2 will then finally forward that data to station B. So as station A roams around, it will enter and exit different BSAs. So here, it's exiting BSA1 and entering BSA2. So at some point, AP2 signal will become stronger and station A will end up reassociating with AP2. And as station A continues to traverse the extended service area, it will keep reassociating with APs that have the stronger signal. And because there are overlapping BSAs, we can ensure that there's seamless connectivity. Now that we've covered basic topology, let's look at what data is actually sent by each station. These are known as MAC frames. Frames are a basic unit of transmission, meaning whenever a station or AP transmits something, that transmission is a series of bits that adhere to a well-defined format. Frames consist of 3 parts, which are the header, the body, and the frame check sequence, otherwise known as the FCS. The frame body contains the payload of the transmission. The frame body is optional as there are instances where the transmission contains no payload. The FCS is the checksum calculated based on the bits inside the header and the body. And the frame header contains metadata about the frame itself. For example, it has multiple MAC address fields to indicate the source, receiver, and destination of the frame. There's also a sequence control field to help with segmenting larger payloads over multiple frames, and there's a frame control field which indicates the type of frame. We'll get into the meaning of what these fields mean in the later slide. In Wi-Fi, frames are categorized as data frames, control frames, or management frames. Data frames carry data from higher layer protocols, so something like IP packets. The higher layer data is encapsulated in the body of the data frame. Control frames assist with the delivery of data frames, thus have no body and are typically found as part of multi-frame exchanges. For example, in this diagram here, this shows a typical multi-frame exchange required to deliver a data frame. Here, the RTS, CTS, and ACK frames are all control frames. The RTS and CTS frames are used to clear the channel, and the ACK frame is used to acknowledge that the data frame was delivered successfully. Management frames are used to manage the wireless network and includes frames for management operations such as scanning, association, reassociation, etc. Recall that the wireless medium is a broadcast medium, so a frame transmitted by a station can be received by all other stations within range. Therefore, each frame needs some metadata to indicate which stations the frame was intended for. In a Wi-Fi frame, this is done through a combination of the MAC address fields and the to and from DS bits. The to DS bit and the from DS bit are part of the frame control field of the header, and they indicate the directionality of a frame. If the to DS bit is set, it means that the data frame is headed towards a distribution system. So this could be a data frame from a station to an AP. Likewise, if the from DS bit was set, it means that the frame was coming from the distribution system. So this could be a data frame from an AP to a station. So the 2-bit combination of the two DS bits and from DS bits determine how the address fields should be interpreted in the frame header. As mentioned previously, each Wi-Fi frame header contains multiple MAC address fields. Each MAC address is 6 bytes long and shares the same address space with Ethernet. There are 4 types of MAC addresses that can appear in a Wi-Fi frame header. The source address is the address of the station or Ethernet node that was the original source of the MAC frame. The destination address is the address of the station or Ethernet node that is the final destination of the MAC frame. The transmit address is the address of the station that transmitted the Wi-Fi frame, and the receiver is the address of the station that should process the Wi-Fi frame. So let's take a look at an example here where station X wants to send a MAC frame to the PC. What will happen is that station X will send a Wi-Fi frame to the AP. The AP will then convert that to an Ethernet frame and forward it to the PC. So within the Wi-Fi frame, it's heading towards the distribution system and not from the distribution system. So we'll need to look at the green row for what the addresses should be. So the source address is station X and the destination address is the PC. But the transmit address is station X and the receiver address is AP1. The rest of this table shows what each address type means for each direction of Wi-Fi frame. Looking at this table, you see that in most cases, one of the addresses is repeated. Therefore, it's not necessary for a MAC header to always include 4 address types. Because not all address types are required, the address for field is optional. Each address field can represent one of the previously mentioned address types or the BSSID. The interpretation of these address fields is determined by the 2 DS bits and from DS bits. So, looking at the previous example, address 1 will be the receiver address, which is the same as the BSSID. Address 2 will be the transmitter address, which is the same as the source address. Address 3 will be the destination address, and address 4 doesn't exist. So now we move on to management operations. Management operations are the actions taken by stations and APs to establish and maintain a connection. This is a cooperative effort between stations and APs, and this typically involves them exchanging multiple management frames. There are numerous management operations, but the main ones to cover are scanning, authentication, and association. To start off, let's talk about how stations discover the existence of a BSS. This is done through beacon frames. Beacon frames are a type of management frame that allows APs to announce the presence of the BSS. Beacon frames are transmitted periodically by the AP, and the beacon interval is configurable. Inside the payload of beacon frames are numerous data fields carrying information about the BSS. This includes things such as the network's SSID, the capabilities of the BSS, and a timestamp used to synchronize the stations in the BSS. Scanning is a management operation for stations to discover Wi-Fi networks. Scanning can either be passive or active. With passive scanning, this involves stations listening for beacon frames from APs of different BSSs. Different BSSs operate at different frequencies, otherwise known as channels, so a passive scan will sweep through multiple channels. Active scanning involves a station sending a probe request frame. If an AP receives a probe request frame, it will respond with a probe response frame. Similarly, active scans will also sweep across multiple channels. The result of scanning is a generation of a scan report. This is basically a list of all discovered BSSs and their capabilities. Furthermore, when scanning, stations can apply a scan filter to filter out BSSs based on certain parameters such as SSID, service set type, etc. Once a station has found a suitable BSS to join, the station must be authenticated before it can join the BSS. The most basic authentication procedure is known as open system authentication. Basically, it's just a simple handshake between the station and the AP. Note that this authentication provides no meaningful security, and it simply ensures that the station and the AP have compatible capabilities. The authentication procedure involves the station sending an authentication request frame, which is then acknowledged by the AP. The AP then sends an authentication response frame, which is then acknowledged by the station. Lastly, the association procedure allows a station to join a BSS. The procedure involves a station sending an association request frame, which is then acknowledged by the AP. The AP then responds with an association response frame, which is then acknowledged by the station. For each station that associates with the AP will assign them a unique association ID, otherwise known as an AID. This AID is then included as part of the association response. The AP must also inform the distribution system about station associations. This is so that the distribution system can keep track of which stations are associated with which AP in order to correctly forward frames to different BSSs. As a station roams, it will need to reassociate with another BSS. Reassociation is similar, and it involves a reassociation request frame and a reassociation response frame. When the new AP receives a reassociation request, it will contact the old AP over the distribution system to let it know that the station has been reassociated. The new AP will then assign the station a new AID, and the AID is included in the reassociation response. Now we'll move on to the medium access method. In other words, how can multiple stations share the wireless medium? The act of coordinating different nodes is known as medium access control, or MAC. And the MAC technique that Wi-Fi uses is known as the distributed coordination function, otherwise known as DCF. The DCF is distributed, so it doesn't rely on the AP to coordinate transmissions of all stations. Instead, the coordination within a BSS is a cooperative effort between all nodes. Other techniques, such as a point coordination function or hybrid coordination function, are built on top of the DCF. However, I won't be covering those other techniques in this presentation. So, some of the features of DCF include using CS-MACA as the multiple access method, having frame prioritization using an interframe spacing mechanism, and also using virtual carrier sensing to allow stations to save power. I'll get into the details of these features later. Firstly, let's take a look at the shared wireless medium. Recall that if two or more nodes transmit simultaneously on the same channel, interference will occur. However, all nodes within a BSS operate on the same channel. Therefore, communication must be half-duplex. Secondly, due to various RF properties such as attenuation, not all stations in the BSS can hear each other. For example, station X here could be transmitting to the AP, but station Z is out of the coverage of X, so station Z will have no idea that station X is transmitting. This is known as the hidden node problem. However, keep in mind that within a BSS, all stations must be within the range of the AP. Otherwise, they wouldn't be able to join the BSS in the first place. So, given these properties, there needs to be some way to coordinate multiple stations so that they don't transmit at the same time. Furthermore, we need some way of dealing with the hidden node problem. Carrier sense multiple access with collision avoidance, otherwise known as CS-MACA, is a method for nodes to share a wireless medium by avoiding simultaneous transmissions. Carrier sense multiple access basically means that each node wanting to transmit must listen to the medium first and wait until the medium is idle before attempting to transmit. However, if the medium is idle, it's possible for two nodes to attempt transmission simultaneously. This is known as a collision, and we can avoid that by having each node use a random backoff timer. So, for example, here's three stations where station 1 is currently transmitting, so the medium is busy. Once station 1 is done transmitting, the medium is now idle. There's an interframe space where all nodes need to wait for before starting their contention window. This is where each node starts their random backoff timer. And let's say station 3 here had the shorter backoff timer, so it starts transmitting first. Station 2 will sense that the medium is no longer idle, and it will know that it needs to wait for the next idle opportunity before it can transmit. The contention window is divided into n slots, where n is a power of 2 minus 1, such as 31, 63, 127, and so on. The random backoff time for each node is determined in terms of slots. So each time a node wants to transmit, they'll pick a random integer r, and the length of their backoff time is r slots. However, CS-MACA alone is not sufficient. The hidden node problem could still lead to collisions. To demonstrate this, let's say we have station X and Y in a BSS. Both stations are in range of the AP, but not in range of each other. Let's say the AP is transmitting here, and after it's done, the medium is idle. Then the contention window begins. Station X and Y both want to transmit something, so they start their backoff timers. Let's say station X had the shorter backoff time, so it starts transmitting first. However, because station Y is completely out of range of station X, station Y will think that the medium is idle, so it will start transmitting as well. The result of the simultaneous transmission is that there's a collision for the AP. Furthermore, only the AP detects a collision. Station X and station Y will have no idea that a collision occurred. Therefore, we need some way to confirm the successful delivery of a frame. The solution to the hidden node problem is a four-way frame exchange. This exchange involves a request to send, clear to send, data, and acknowledgement frames. The RTS and CTS frames are used to clear the channel before transmitting a data frame. Using the same example above, if station X transmits an RTS frame, then the AP will send a CTS frame back to indicate that the channel is now clear. However, if there was a collision at the AP, it will not respond with a CTS frame. This indicates to station X that it needs to retry at some later point. Likewise with the acknowledgement frame, if station X sends a data frame to the AP and there were no collisions, the AP will respond with an ACK frame. The lack of an ACK frame indicates to station X that a collision occurred and it needs to retry. Note that the four-way exchange only deals with collisions, but it does not prevent collisions. Something else to consider is how do we make multi-frame exchanges atomic? In other words, how do we make sure that another station does not send an unrelated frame during a multi-frame exchange? For example, here we have a four-way frame exchange where the AP is sending a data frame to station X. What we expect to happen is that station X should respond with an ACK frame. However, when the medium becomes idle, what if an unrelated station Y has a shorter backup time and ends up sending an unrelated frame? So this could mean that the four-way frame exchange gets interjected by some random frame. Essentially, there needs to be a way of ensuring that the multi-frame exchanges are atomic. And this is achieved by using different interframe spaces. So if you recall, the interframe space is a period of time following the end of a frame. By having shorter interframe spaces for certain frames, we can guarantee that those frames will have priority. Wi-Fi has multiple lengths of interframe spaces, but the ones we're going to discuss today are the short interframe space, otherwise known as CIFS, and the DCF interframe space, otherwise known as DIFs. CIFS is the shortest interframe space, thus is for the highest priority frames such as CTS and ACK frames. This makes sure that the frame exchanges are atomic. This is a longer interframe space, followed by a contention window to allow for stations to contest for the wireless median. This is typically used for the first frame of most multi-frame exchanges. The last medium access concept we have to cover is carrier sensing, which is the method used to determine whether the medium is busy or idle. Firstly, we have physical carrier sensing, which is when a station keeps its radio powered and is actively listening to the medium. However, keeping the radio powered is power intensive, and the hidden no problem could also lead to false idle conditions. Therefore, Wi-Fi also has virtual carrier sensing, which is the method of tracking whether the medium is busy without the need to physically sense the medium. The way this is achieved is through the network allocation vector, or NAV. The NAV is basically a timer in each station, which indicates how much time is left until the medium is idle. This allows the station to shut down its radio to save power and power it back on only when the NAV expires. So, how does the NAV know how long the medium will be busy for? Recall that there was a duration ID field in all frame headers. This field basically indicates how long the medium is going to be busy for. So let's take a look at an example. Here we have a typical four-way frame exchange between the station and the AP. As the station sends an RTS frame, the RTS frame's duration ID field will indicate how long the medium will be busy for the entire four-way frame exchange. And just in case there was a hidden node, all stations are within range of the AP. So when the AP sends a CTS frame, the CTS's duration field will indicate how long there's left for the four-way frame exchange. So the result of this is that all nodes within the BSS will have their NAVs updated as a result of the RTS and CTS frames. So they can go ahead and shut down their radios and wait until the NAV expires here before they power it back on and sense whether the medium is physically idle or not. Now we get to the physical layer. The physical layer is quite complex, so I won't be able to cover it in detail. So, if you didn't already know, wireless communications use radio waves. And in the electromagnetic spectrum, radio waves occupy the lower frequency end of the spectrum. The radio spectrum is split into bands, and the usage of most bands is strictly regulated and requires a license. However, there are certain bands which are not licensed. These are known as the industrial, scientific, and medical bands, otherwise known as the ISM bands. The ISM bands that Wi-Fi uses is a 2.4 GHz band, which actually ranges from 2.4 GHz to 2.4835 GHz. And there's also the 5 GHz band, which ranges from 5.725 GHz to 5.875 GHz. And within the ISM band, Wi-Fi divides up the band into multiple overlapping channels. The number of channels differs depending on region and country. However, all stations within the BSS must operate on the same channel. So the point of multiple channels is to allow for channel selection. Network designers can pick channels to avoid interference from the environment and also neighboring BSSs. Typically, what will happen is that each BSS will use a non-overlapping channel from a neighboring BSS. For example, channels 1, 6, and 11 are non-overlapping. So when selecting channels for a BSS in an extended service set, we need to make sure that each BSS uses a different channel that doesn't overlap with the neighboring BSS. So that's all the content we have time for in this presentation. However, Wi-Fi is still a complex protocol and there's a lot more to learn. As a follow-up, here's some further topics I recommend you take a look at. Firstly, there's some topologies that we didn't cover, such as the IBSS and MBSS. For Mac frames, there's also the idea of fragmenting. And for security, I suggest you take a look at the WEP and WPA protocols. For power saving, there are two methods you can take a look at, which are the PS pole and target wake time. As for modulation schemes, this could be entirely its own topic, but you can take a look at some modulation schemes used in the Wi-Fi protocol, such as DSS, OFDM, OFDMA, and QAM. And finally, if you're interested in getting a copy of the slides, you can find them on my GitHub. And in terms of beginner-friendly books, I suggest the Definitive Guide by Matthew Gass and the CWNA Guide by Coleman and Westcott. Large parts of these presentations were based on the contents of those books. So, thanks for watching, and I hope you learned something today.